Is everybody comfortable with the chair that was on your left here being the higher energy? You could have just taken account of all the axial versus equatorial bonds, right? And the fact that you had 3 axials, you know that had to be
Dr.
higher
Cooper,
energy than the one that had 3 equatorial. Yes, ma'am.
can you start the recording now? Because I have to go to a meeting.
Yeah, it's recording right now. It says you are recorded.
Okay.
Well, I see it on my side, it's recording. Yes, ma'am. If you gotta leave, I know some people got classes, they went expecting to stay past noon. So if you're in the class and you gotta go, you can. But if you wanna stay on the line, just get to this test. All right, any questions about the chair that had all those axial extensions being higher than the one that didn't? Any questions there? All right, the last question I already answered. I think somebody stopped by my office and just recorded my handwriting. Go ahead.
Did you do the one with the higher boiling point?
Yeah, that's what I'm working on right now. All right. So the trick of this question is that you have to look. They're isomers, but one is branched versus the other. I tried to draw as best I could. The one that's on the left is branched, and the one that's on the left is not as branched, right? It has a branch and it's kind of a linear tail. So you guys want to remember the relationship between branching and intermolecular forces and boiling points, right? What's the rule there? The more branched you are, the what you're boiling.
The higher.
Not the higher. The lower the boiling point, branching does. So keep that in mind. Branching will lower your boiling point. And conceptually, you guys got to know why. Why would branching lower the boiling point?
There's more intermolecular forces.
All right, so it's not more, but it's less intermolecular forces when you branch. All right? Branching causes things not to pack effectively. So when I branch, I break up opportunities to pack. That's less intermolecular forces, and I boil higher. So the question was, give me the higher boiling one, right? Not the lower boiling one. So the higher boiling one would be which one? The one that's more branched or less branched? The one that's less branched, right? And out of these two, this is the one that's less branched. So it's higher boiling because it's not as branched. It will have more intermolecular forces, and it will have a higher boiling point. What are the intermolecular forces that are present in this molecule?
Van der Waals.
Yep, there you go. Thank you. There's only one force possible. That's van der Waals. There's no polar atoms. There's no hydrogen bonding present. Good. All right, let's assign this configuration. Can you guys help me out? I got a 3-way tie. I see carbon, 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 right? And I see an H. I can assign one priority already. Which one is that? Yep, the H. Is everybody comfortable with that? All right, so let's try to break this tie. I got a carbon that has an oxygen attached, a carbon that has an oxygen attached, and a carbon that has another what attached?
Carbon.
Carbon. All right, let's put a C here. Okay?
But.
So who breaks that tie down?
Don't they all have an extra carbon too?
The one down here has another carbon, but the other two has oxygen and carbon. So I can already break that tie off of that, right? There's one different than the other. So who wins out of oxygens and carbons? Oxygens. So up top, this has to be now 3, right? Mm-hmm. All right, it's not going to be higher than the other 2. All right, so I got 3 up top. So now I got one carbon that has a single bond to oxygen and another carbon that has a what to oxygen? A double bond. So how do we count the double bonds as having how many oxygens? 2 oxygens. So this really has 2 oxygens attached, and this only has 1 oxygen and an H, right? Right. So who wins?
The double bond.
The double bond is going to win, and this would be A2. All right, so if I look at my rotation of atoms in purple, 1, 2, 3, this is clockwise or counterclockwise? This is counterclockwise, right? Do I need to flip what I see?
No.
This is good. Smallest symptom is where? In the back. Counterclockwise, so this automatically has to be in S configuration. Is everybody cool with this being S? Okay. Let's try this in the next example. What's my priorities here? Who's first?
Dr. Cooper, I can't see your screen anymore.
Okay, let me try to stop and reshare. Give me 1 second. All right, can you guys see my screen?
I still can't. Okay, can I leave out and call me back into the group?
Yeah, I'll try my best to call you back. It's gonna be hard, a little hard, but I can do it. Oh, okay, I see it. I can do it here. Okay, I know how to call you. Oh my, the way this things are set up. Yes. Did she leave already? Who was? I think I knew who that was. Third. All right, let's call her. Okay, let's try the next one. Who's the highest priority now?
Broken.
One more time. Try one more time.
Me, Charles?
Yeah. Yes, ma'am. Who's the highest priority? Out of iodine, chlorine, bromine, and fluorine.
Oh, I know.
Iodine is going to have a 1. All right, who's next? All right, who's next?
Sorry.
And who's last? All right, so I'll look at green. Let's see. 1, 2, 3. This looks also great. Let's count that.
What happens if I'm like, which way to go? Because,
Always 1, 2, 3. Just one or other.
well, you can go 1, 2, 3 from left to right. You can go 1, 2, 3 right to left.
Honestly, one way.
If we got 3 at the top, right? Oh, okay.
You got to go
So,
to 1, 2.
okay. That's it.
All right, this is clockwise, so this looks S, but I need to do what? Look, let's see.
You can count it.
That's right.
Oh, okay.
It's S, but
So
you
it's
flip.
being turned to off.
Okay, any questions there?
You gotta go to Colombia.
Oh, Ms. Lewis, you got your mic on. All right. Let's try to solve this problem if we can. All right, so first of all, when you guys are looking for relationships, look for your basic stuff first, as soon as you can. That'll be the biggest help. So what are some of the basic things? Do they have the same number of carbons, oxygens, etc.? Do they have all the same atoms? And hopefully you guys can tell that these 2 molecules do have the same weight. Same molecular form, have all the same atoms, right? So that means that they do have some relationship. If there was any difference in the number of atoms or etc., then I know that these will have to do what? There will be no relationship or different molecules. So keep that in mind. All right, I definitely like to use that trick when it comes to stereochemistry, right? Students spend all this time doing RNS when the 2 molecules didn't have what? Any relationship. You could have automatically said what? Different, move on. So keep that on the test. Keep that in the back of your mind. If you're working hard on a problem, you probably did what most likely? overthought that question. I try to make the test that you can do it in an hour, right? I'm not trying to have you doing R and S the whole exam, right? Okay, so these have the same molecular formulas, right? And they have atoms connected the same way. Can everybody see that? So if I look at the second carbon in this 4-carbon chain, it has a what attached to it?
Okay.
An OH. Both molecules have that same connectivity. Can you guys see that? All right, so that means if I have the same connectivity, they cannot be what now? Constitutional isomers, right? So I'm just working down the list. They're not different, and they're not constitutional.
You gotta say one more time where they're not constitutional.
Because they have the atoms connected the same way, right?
What you pointing at? What you pointing at?
Oh, right, okay, I wasn't pointing at nothing. I was talking, I'm sorry. If I go 1, 2, 3, 4, and 1, 2, 3, 4, right? There's 4 carbons in that chain. And on carbon 2, they both have what attached? OH.
Substituent.
Right?
Oh yeah, that.
Yeah, OH, that's right. You can call this extension if you want, that's fine. All right, so because carbon 1 has 3 hydrogens that's bonded to carbon 2 that has 1 hydrogen and an OH, carbon 3 has 2 H's and carbon 4 has 3 H's. I didn't change the connectivity between these 2 molecules. They're all connected the same way. So that means that they are not constitutional isomers. But if I move an H or if I move an O, then I know that the relationship would have been between these 2, if they had the same molecular formula, constitutional. Right? Constitutional isomers differ by connectivity. Keep that in mind. Same molecular formula, there has to be a relationship. All right? If they move atoms differently in connectivity, it's constitutional. So this appears to be a difference in just how things are oriented. How?
The part of it.
That's right, which is 3-dimensional information. So we say that things that have the same molecular formula but differ only in 3-dimensionality are called what?
Stereoisomers.
That's right, stereoisomers. That's the definition of a stereoisomer, is that we share all the same connectivity, we just differ in space. All right? Now, sometimes this is tricky. Can you look at this and determine if this is a mirror image or not?
Yes.
Okay. Is this the mirror image?
Yes.
Oh, okay. See, that's where you guys, you're not convinced yet. You guys can't tell this is the mirror image. If this was the mirror image, that OH had to be still on the wedge. Okay? So let's work out. So for those that are like me, I never trusted that ability when I was in college. When I did this in college, I never trusted that ability. I always assign what you think. R and S. All right? For it to be true enantiomers, the stereocenter 2 has to be R in one structure and what in the other structure?
It's
S. That's the relationship between enantiomers. So let's go ahead and assign configurations. So for carbon 2, 1 has to be the first priority, or the oxygen is the first priority. This alpha group will be priority 2. The methyl group will be priority 3. And there's an H that's on the way, on the dash, right? If I look at the rotation of things, right, it looks like this. This is clockwise. So this will be assigned in R configuration. Any questions there? All right, let's try the other side. This oxygen is still this 1. The alpha group is still 2. The methyl group is still 3. And this time I got a H on a wedge. On a wedge, and this will be assigned 4, right? If I look at the rotation that I get from this one,
you got to switch.
this looks counterclockwise, which is defined as an S, But because my small group is in the front, I have to do what? Flip it. So this is going to be a sign of what? An R.
So it's the same,
So I got an R and another R. What's the relationship between that?
same.
That's right. These two molecules are exactly the same. Right? So then that means that this molecule will transpose perfectly back. It's not my non-superimposable mirror image. Right? Okay. If that OH was on a wedge, that would have been the perfect mirror, and that would have been non-superimposable. All right, this next question, to move between a Fisher and a Newman, you don't have to do. Okay?
So we don't have to know how to do the same.
No, if I give you a Newman projection, you will not have to do stereochemistry for Newman. All right? That's a mistake of when I first got here. They told me students don't need to know all that. So, okay, so I just changed. All right, so don't worry about that. You don't have to know how to do stereochemistry from a Newman projection. But if you wanted to go to grad school in chemistry, it's a good skill to have. Don't worry, you learn that in grad school. Trust me, you'll be doing some questions. Your advisor like, you learned Newman projections in undergraduate, right? Go ahead and get your model kit and start working on those. Okay, let's work on the next one. This one you are able to do, right? This is a perspective drawing, and there's a Fisher projection. So can you look at these two compounds and determine the relationship? Let's go through our list. Do they have the same atoms attached in both molecules?
Yeah.
Yeah. All right. I'm going to call this carbon A, and this is also the carbon A, right? So carbon A here has this aldehyde C double bond OH. Same thing here, right? So these two groups are the same. Then I have OH. This also has an OH. Then I have a methyl group. This is a methyl group. And both also have a what? An H, right? In this case here, H is dash. All right, so they both have the same atoms attached to carbon A, right? So I know they cannot be different. And also, because they have the same connectivity, they cannot be what else? They cannot be constitutional, that's right. So that means that there might be a stereochemical relationship. So they could be stereoisomers. Can you look at these and tell if this is a non-superimposable mirror image of each other? To be honest, I cannot do that. If you can do that, you're going to have a great career as an organic chemist, right? You're ready to go to make millions of dollars. There's a lot of problems that they pay people to solve, right? Exxon used to call us all the time. You guys want to come out here, try to do some stuff? And those guys sometimes don't come home.
Who you used to work for?
I don't want to say, I never worked for Exxon. I didn't work for Exxon, but they were recruiting at LSU. That's obvious, right? That's one of their hubs. It's good money, but some people don't make it home, and then I know stories about other things I don't want to say, right? But some families don't make it through, right? If you're married, and that could be a strain in a relationship, right? Some people want a typical, I want my husband around with the kids, a family, and we do things together. You might be a husband that never comes home, right? You might be 6 months out at sea trying to solve problems. That could be not the ideal situation. But also, those guys, I know they got to send in reports, and they get in trouble if things don't work. And if you get a couple of bad notations, your job could be in jeopardy as well. So that's the stress to have a job and then go from having a job, making decent money to go away. No job. But it's good if you're single. You single man, you good, right? You're good for a little while. I would work for that 10 years and then go get married later. You'll be good. All right. That's my statement for the day. That's just my statement for the day. All right, can we assign a configuration here?
Gotta do the priorities.
All right, let's do the priorities. I'm gonna work on the structure on the left first. My oxygen is gonna be away. 1, right? We cool with that? And then I got carbon, carbon. Who wins out of my 2 carbons? The carbon is double bonded to a O, right? So that's gonna be 2, it's gonna be 3, and then there's an H there, and I have to worry about. If I look at my rotation, this looks like what? That's clockwise, right? Do I need to flip this? No?
No.
So, a straight R. Very, very good. I'm starting to feel better now about giving this test on Monday. I'm starting to.
Dr. Cooper, I can't see a screen on the.
Okay, give me 1 second. Let me turn it off, turn it back on. It's easy from the iPad than it was when I was in the computer. I can't believe I recorded myself saying that. My homeboy gonna be upset. I do got a friend that works at Exxon. I'm gonna try to get him to do a seminar. I'm gonna try to get him to do a seminar next semester. I will. I'll work on that.
Man, you funny.
I'm gonna have him do a seminar next semester. He works at Exxon. I'm gonna talk to him tonight. He was like, cool, what are you telling the kids? I just told the truth, brother, man. All right, can you guys see my screen now?
No.
Okay, give me 1 second.
No.
No.
I started the broadcast. All right, what about now?
Yes.
Okay, great. All right, let's do the next structure. Same. Go ahead, I'm sorry.
I still can't see it. Yeah.
Who said they can't see this?
Sorry.
Ms. Moore? Ms. Moore, can you go ahead and log out and I'll call you back?
Okay.
All right, let me call Ms. Moore.
Your next class.
I'm done for the day. I just got my research students coming at 2. Hopefully we could be done by 2 o'clock, right?
Oh, Lord, we're supposed to be done by 1.
Oh yeah, I'm hoping to be done by then too.
I can see it now.
You can see now? Great, Ms. Moore. Yes, we want to be done soon. I'm gonna get some food today. And, all right, oxygen is 1, aldehyde carbon is 2, methyl group is 3, but my H here is on a wedge. On a wedge, right? Is everybody comfortable with that because it's horizontal? So if I look at how things are going, this looks like it's this direction, which is what? Counterclockwise.
Counterclockwise.
That's right. And I would have given that a S, but I need to flip, and this has to be, so this stereocenter is also R. So what's the relationship here? Exactly the same. All right, let's do the next problem right quick. So I'm just trying to read some of these. All right, so what's going on? First of all, let's go through our list. It's not overwork, we don't have to. Do we have all the same atoms in the 2 molecules presented to us? And I'm working up here with these 2 things here.
No.
So let's count the number of oxygens. How many oxygens do I have in this first structure?
Sure.
This has 3 oxygens, right? How many oxygens do I have in the second structure?
2.
Only 2 oxygens. That's a big sign. What is that telling us?
Yeah.
They automatically have to be what?
Yeah.
Isn't that a blessing?
Yes, it is.
That would have been hard to do what for this molecule? R and S, right? I know.
That's the one I had trouble with. That's the reason I couldn't solve.
Yeah, I do that deliberately, but you should know it's a trick. If you gotta work that hard to solve a problem, you know Dr. Cooper's not gonna do you like that. But I do that deliberately because I'm thinking, oh, you didn't out for something simple, right? You missed something very simple. And you just wanted to work hard. There's some people that love to solve those things, right? Just want to go RNS, that's all. Okay, but if you want to, out for hours, we can go through this and actually assign all those stereo centers. All right, but there are two different molecules off the bat. They're not the same molecules. So there's no relationship between the two. And I was just curious for this question in relationships. All right, is there any relationship between these two molecules? All right, so I would try to translate the three-dimensional information back, right? And typically what I do first is to make sure, do they have the same atoms connected in the same places? So I can go 1, 2, 3, 4, 1, 2, 3, 4, right? At carbon 1, this is isopropyl. And carbon 1 over here is still isopropyl. Over here, this is terbutyl group. Over here is also terbutyl group. So they got the atoms in the right locations, right? So for the most part, they probably have the same atoms and everything connected the same. So I just need to check the relationships of sustentions. This is on a carbon that's pointing up in an axial, so this means top. And over here, this is pointing on a carbon that's pointing down, so it's equatorial. This also means the top. Okay. So over here, I got an isopropyl that means wedge, so that also means what? Top, because wedge means top. And over here, I got a terbutyl group that's on a dash, that means what? Bottom, because wedge always means bottom. So this is a cis molecule, and this is the trans version of it, right? So whenever I see cis and trans, what do I call this relationship?
Geometric.
Right, geometric. And I didn't have enough time to teach you guys this. I was going to teach you in the next chapter that geometric relationships are also known as diastereomers. It's a stereoisomer that's not my mirror image. That's a diastereomer. So cis trans are also diastereomers.
So I could put either diastereomer or geometric.
Yep. Either or would work here.
And so apparently it's two something centers on these.
No. It's not diastereomers from chiral carbons. It's diastereomers as a whole. I know that could be tough to think about. When you think about diastereomers, you think about having different chiral carbons that have different configurations. Right? One stays the same, one changes. Right? These are not necessarily diastereomers because of those chiral carbons. It's overall the relationship between two molecules. So because I got two sustentions that are cis and the other two that are trans, to each other they're geometric or diastereomers. So that's why we use both words there, geometric and diastereomers. Geometric isomers are just also fundamentally defined as diastereomers.
Okay.
All right, let's work on defining stereocenters. Let me get my pen and work. Sorry, I already worked on this. All right, to find chiral centers, you guys know, I'm just looking for areas. Hello. Okay, sure. See ya. Okay. I'm looking for carbons that have 4 different groups attached, right? Okay. So I'm hoping that everybody sees that only the carbons that have chlorines we should consider right now. Everything else has 2 hydrogens, so by default, it cannot be chiral. All right, is everybody comfortable with that fact?
Yes.
All right, so we just need to double check those carbons with chlorine. So let's take a look at this carbon first. If I move over just 1 and 2, I get a carbon that has a chlorine. If I do the same thing over here, go 1, 2, do I have a carbon with a chlorine on that one?
No.
So those 2 chains coming from that carbon are completely what? Different. And there's also a what here? An H. So I got this chain on the left side that's different than the chain on the right. So that means that this carbon has to be what?
Carbon.
It's carbon. Any questions with that? I'm gonna put a star here. This is a carbon. All right, let's check this carbon. I go 1, 2, I get chlorine, right? And I go 1, 2, do I get chlorine? So this carbon right here, is it chiral now? So the chain, the upper chain is different than the chain that's on the bottom, right? So I got 2 different chains there. Chlorine is different, and this is also what on that carbon? An H. So that means that this carbon is also what? Chiral. Star here. So that's a chiral carbon. All right, let's check to make sure that this carbon is carbon. If I go 1, 2, 3 before I get to a carbon with a chlorine, right? If I do the other chain, 1, 2, 3 before I get to a carbon that has a chlorine, they are both what? They're identical, right? They have the same length chain. So could that carbon be chiral? It can't. So this is not chiral. So for this molecule, there's only 2 chiral carbons. The 2 carbons I just showed. Okay? Is everybody kind of comfortable with that? Okay. Let's move on to this next example, right? Is this carbon I'm going to circle in purple? Is that carbon chiral? Let's take a look. It has an oxygen, a methyl, a carbon, and a what else?
A methyl is not.
An H, right?
Well, not.
So it has this group, that group, and that group. Are there 4 different groups? Yeah. So this carbon is chiral.
How do you have 2 methyls?
It's a carbon that has a methyl. It's not a methyl directly attached to that carbon. It's just a carbon with methyl. Right? I didn't circle, so when I circled that, I did not circle this. That's the methyl right there, right? It's a carbon before you get to it. Okay, what about the other side? Can I erase the purple circles? So if I want to look at this, what do I got? A CH3 group, an oxygen, a carbon that has 1 H and a methyl, and a what else? And a hydrogen. Are there 4 different groups?
Yes.
Yeah. That carbon is chiral. What about that carbon right here? My iPad's gonna die. Show.
No, it's not, because it's not a carbon.
Okay. You sure it's not a carbon?
It's oxygen.
It's a carbon there, okay. It's carbon, but it's a carbon attached to 2 what? 2 oxygens, right? Is that what you're
Oh,
saying?
never mind. You point at the methyl. The one with the methyl.
Yeah, that carbon that's a carbon that has a methyl, but it has 2 oxygens, right?
Yes.
So automatically it can't be chiral. So this is not chiral. All right, let's take a look at this molecule here. Is there any chiral carbons here? So obviously I got a wedge up here. I'm going to check that. I'll go 1, 2, 3, 4 and I hit a carbon oxygen double bond, I go 1, 2, 3, and 4. All right, so those two chains trace back differently, right? So that means that they are different. I have an OH and a H and dash, so that carbon has to be what? It's carbon. Okay. What about, is there any of the carbons that have 4 different names attached, or potentially? What about here? These positions, are they chiral? Let's say, look, I go 1, 2, then I hit the carbonyl, right? Or I go 1 and then 2, and I hit the carbonyl, right? So that means that they do have different chains, right, on either side. Right? Actually, I did that kind of weird. Let me do it like this. For this, I need to focus on one stage at a time. So for this one is 1, 2, 3 before you get to the carbonyl, and the other one would be 1, 2, 3. Okay. But carbon 1s aren't the same on these two chains, right? Versus. All right, those two chains are different. All right. Well, what about up top? So I got 2 different chains, an H, and then I have to have a, excuse me, a what up top? Or this chain here. So for this carbon here, it is what? Also, I got a chain in blue, a chain in red, and a chain in purple, and that H popping up, right? All 3 of those carbon chains are different, right? So that makes that carbon chiral. And you can do the same thing on the other side. So this molecule has 3 chiral carbons attached. Okay? Is
Dr.
that
Cooper, I have a question.
sure?
So it doesn't matter if the 2 carbons that are chiral have the same type of groups, as long as they all have 4 different ones.
Yes, they should be all, 4 different. The chains are different here, if you want to say, right?
I'm talking about, like, say we didn't have the bottom and we were just looking at the top part. They both have the same amount of carbons in between them and the hydroxide group.
Oh, yeah, sure, they do. But they're at 2 different positions, right? If they were attached to the same position, they wouldn't be chiral going to that carbon that had the OH.
So since one is like 3 and the other one is 4.
Yes. So the chiral, this chiral, I think I understand what you're trying to say, and I hope this helps. Because I have to count that carbon, when I think about only this one, that carbon is chiral. And so carbon 1 chain, so if you think about a chain in red here, it has a chiral carbon there. And the chain in blue did not have a chiral carbon, so that makes those 2 difference. And it didn't matter that they connect back. But purple, to get back to, would have to also go through that chiral carbon. So that chiral carbon throws off the symmetry, right? If you're just thinking about one of those stereocenters. If you want to, just break it, think about breaking things right here. I understand, I think I understand the relationship that you see, sure. This carbon is 1 away from the carbon that has an OH, and on this side it does too. But we're not looking at these 2 carbons together. We're looking at one at a time. So for this carbon.
Yes, that's what I was asking. Yeah.
Okay, yeah, you're looking at one at a time. Okay, let's try the next question. Can we assign R and S for the stereogenic centers. Hopefully everybody's comfortable with this and that being the stereogenic carbons for this bond. So anytime you got Fisher, the crosshairs are going to be, there's no other carbons in the molecule. Everything else has multiple H's. Carbons with multiple H's. Okay. Or multiple methyl groups. This carbon has 2 methyl groups. All right. Let's do the one up top if we can. Can you help me assign the priorities? Who's first out of chlorine, methyl, H, and all of this?
The big group. Carbon.
Not that carbon. So it's carbon, chlorine, carbon, H, right? So who wins out of carbon, chlorine, carbon, H? Chlorine, right?
Chlorine.
So chlorine's going to be 1. Then my carbon that has a bromine beats a carbon that just has an H, right? Excuse me. Not corona. 2. This is 3. And that's 4.
Yeah.
All right? So because my H is horizontal, it has to be on the way. A wedge. So I need to flip what I see. So this looks like it's going to be clockwise, but instead I flip it, and that has to be a S configuration. Is everybody comfortable with that? Okay. So let's do the bottom 7 if we can. All right, so my 4 groups to this carbon are methyl, bromine, isopropyl, and all this jazz at the top. Okay, so who wins out of bromine, carbon, carbon, or carbon? Who wins initially?
Bromine.
So bromine again would be 1. Or, I'm sorry, not again. The last one's a chlorine, this is not bromine. All right, who wins out of carbon, carbon, carbon? So this is carbon that has an H only. This is carbon that has another carbon, but this is carbon that has a chlorine. So who wins?
Chlorine.
Carbon with the chlorine wins, that's 2. Then carbon H or carbon carbon? Carbon carbon, and then carbon H last. So if I look at this rotation from 1 to 3, this looks what? Counterclockwise, right? My smallest group is on the way, on the dash, so it's good as is. So because it's counterclockwise, this is going to be what configuration? S configuration, right? Any questions here with that configuration? Oh, it wanted me to name the molecule. I'm sorry.
Oh,
Let's go back and name the molecule. I definitely need the stereocenters. All right, I need to find my longest chain and work with that.
talk about
The longest chain is pentane.
Okay, good. Did I number, is that the longest chain? Did I number it correctly?
I mean, I can't see, but that's going straight up and down, right?
No, not going straight up and down. You gotta bite into that isopropyl to get those extra carbons. All right, this is not numbered correctly. I did that on purpose. All right, if I look at this, I have a bromine on carbon 3, right? But if I number starting up top, I will have a chlorine on carbon 1. So you want to give those higher priority carbons if you can, the lowest number. So in this case, it should be 1. 1, 2. Okay. And don't forget that there's an extra methyl group on carbon 4, it's branched. Right? So it looks like this.
So is it group 6?
No, it's not 6. It's just 5, and and the other methyl group is a suspension. Okay? So now I'm gonna go ahead and name this molecule, all right? Alphabetically, who comes first? Chlorine, bromine, or methyl?
Bromine.
Bromine, so I'll say, let's go ahead and start with our stereocenters first, I'm sorry. So this is 2s, 3s, 3 bromo, 2 chloro, 4 methyl, pentane. Okay. Not too bad, right?
Okay, so why is there methyl not on the third carbon?
It's on carbon 4. Oh, there's a methyl, I'm sorry. There's a methyl on carbon 3. I skipped, I didn't even, I missed that. Thank you, I'm so sorry. That's a mistake, there's another suspension here. I should have boxed all my suspensions, I'm sorry.
So 3, 4 dimethyl.
3, 4. Sorry about that. All right, I'm gonna run and get my charger for my iPad. Give me 1 second. It's not gonna last. Okay, I'm back with some power. My iPad is charging now. All right, can we do RNS and describe any relationship between these two molecules? Let's go ahead and try this. Carbon 2 on the left, I'm going to try first. Chlorine is the 1 priority. Carbon that has an oxygen is the 2 priority, and methyl is the 3 priority. There's an H that's on a wedge. That's very important that you know, but you need to flip what you see. If I look at the rotation of that, that looks counterclockwise, right? So this would be typically S, but I need to flip, so this is going to be R. Is everybody comfortable with that?
Yes.
All right. Let's go ahead and try the bottom carbon. Oxygen is 1, carbon with chlorine is 2, methyl group is 3, and there's an H that's on the way here. Dash, so I keep what I see. If I look at the rotation of 1 to 3, that's what? Counterclockwise, so that's going to be given a S. All right, any questions there?
Okay, this is getting easier.
Okay, let's try to do the chlorine again. Carbon 2. You won't let me switch the color back. Okay, I'm gonna do 1 chlorine, carbon, oxygen, 2, methyl group, 3, there's an H that's on the way here. Wedge, so I have to flip what I see. If I look at the rotation here, this looks clockwise, but because I need to flip it, it's gonna be a S, right? Let's try the carbon. Oxygen has to be 1, carbon with chlorine, priority 2, methyl group is 3, and I have an H that's on the way this time. A dash, right? So I keep what I see. This look clockwise, so this has to stay R. So what happens between the centers here?
They are.
My 2 was R and it went to an S, and my 3 was S and it went to R. So because I flipped both enantiomers, this is, if I flip both centers, this is what enantiomers. Okay. Any question here? I certify this way. Now this is crazy. My signature is the only thing that looks normal on my pad. Everything else looks kind of weird. All right, is there any questions? All right, I will do this with normal handwriting and send this to you guys, okay?
Thank you.
No problem. Monday, we definitely have to take it. I'm probably gonna have to start my other lecture on Monday though, but we'll see, we'll see. I'm pretty sure you guys might have questions. It's all right, we're not behind. I know you might think about, well, you've been pushing this date that, are we falling behind? Actually, I've been looking at the course material. We're actually not that weird. Even with all this stuff, we're in the normal spot. So it's gonna work out fine.
Dr. Cooper,
Yes, ma'am.
don't forget to check your email about the lockdown.
Oh, Miss Joseph, I'm gonna call you on Teams right after this.
All right.
All right, is there any questions, anyone? Currently on the line? If not, I'm gonna go ahead and cancel this. It's almost 1 o'clock. Okay, good. See you guys next class. I'm gonna try to download attendance here.
Dr. Cooper, you gonna upload this weekend?
Okay, yep, I'm gonna upload it today. I'm gonna try to download it. If it downloads to my computer quickly enough, I can upload it. Sometimes it works, sometimes it doesn't. I'll just have to see.
Okay.
All right, I'm gonna end the meeting here. And again, I need to call somebody. That was Joseph. I'm gonna call you right now, Miss Joseph, as soon as I end this. All right, you guys have a good day. Is it downloading my stuff? It's not downloading the video. Come on here. Oh, I gotta stop the recording.